ADP and PI are going to come in up from the matrix side, and ATP is going to be released on the matrix side. But it doesn't do the cell any good, or the body any good, to have a whole bunch of ATP accumulating inside the mitochondrial matrix. It clearly has to get out. So ATP has to get out, while ADP and phosphate have to get in, right, during this fuel burning process. Okay? Any questions so far? Yeah.
What's the pH of the matrix?
The pH of the matrix is around 7.4. I'll check on that, but that's approximately what it is. And the delta pH across the membrane is about 0.4 to 0.6 units. I'll have that for you in detail as well.
It says 7.8.
7.8.
Just as a quick, who knows? I'm not trying to wrong you, just.
Okay, 7.8.
Who knows?
Okay. Yeah. Okay, other questions? Yeah.
So does A and P have to be related to ATP?
Does ATP?
A and P?
Oh, yeah, AMP is not involved in this process at all. So if there's an AMP generated from an enzyme as part of metabolism, in order for it to get imported to be used, it has to be first converted to ATP. Yeah. Okay, so last term you probably hit some mechanism of membrane transport. Is this slide look familiar? Okay. So you could ask, where is this mechanism that we're talking about? Clearly, it's involved in the membrane. We have a pH gradient across the membrane, and we're going to be using the pH gradient to drive ATP synthesis, which basically means that the protons are going to move through the membrane. Okay, so that's what that process means when I said use the pH gradient. Right here. That is to say, run it downhill. That's what using it means. Right? We build it up, and that's unfavorable. Right? We create a delta pH, and then we dissipate the delta pH by letting the protons run back in a thermodynamically favorable direction, which is to say, go back in. Okay. So when they come back in, that's favorable, and that allows the synthesis of ATP to occur, which of course otherwise would be very unfavorable, right? Because this otherwise would be delta G0 prime would be minus 30.5 if you consider it in isolation to make ATP. So if you look at this membrane transport figure here, these are ion channels, but ion going down electrochemical gradient. Maybe you have a gated channel for an ion. Ionophore mediated transport, again, down a gradient. This is a simple diffusion, down a gradient. Right? Then you could have a facilitated diffusion process with a protein just to get something in, right? But this is also down a gradient. So these are all already thermodynamically favorable. Right? Here we've got something called secondary active transport, right? Where we've got an ion that's favorable, moving downhill, and it's coupled to something unfavorable. Right? So what it's coupled to in this case is the transport of this molecule S against its gradient. Okay? So if you want to look at this situation as being parallel, the ion would be a proton coming into the matrix of the mitochondria. This would be the matrix, and this would be the inner membrane space. Proton would come in, and instead of something else coming in with it that is otherwise unfavorable, you have ATP getting made here, which is, of course, also unfavorable. Right? Here's a process by which ATP is hydrolyzed to bring something in that's unfavorable. Right? Or you could turn this around and say, okay, this is favorable, proton gradient is favorable, and now we can run this the other way. Right? So ATP synthesis, proton gradient is downhill, favorable, and drives that unfavorable reaction. Yes, sir?
So I thought that it was secondary active transport because the ion gradient, which is going down, the ions which are going down in their concentration gradient, that concentration gradient is primarily being constructed by a primary active transport. Is that accurate, or does it not have to be that way if you just have a gradient and
I think if you have a gradient that's otherwise favorable on its own without the need for active transport, then it can still function as a secondary transport. Maybe there's a formal definition that I'm not completely acquainted with, which would be what you said. I don't think it's not that important for our purposes today.
okay?
But yeah, I'm showing the slide because I'm hoping that what we're talking about today can connect up to something you learned last term in some meaningful way, right? And these are all the different mechanisms that were mentioned before. And so ATP synthase fits within this general conceptual scheme, even if it doesn't have a specific example on that slide that really directly corresponds to what's going on. Any other questions on that? Okay. So what we have when we have a proton gradient is we have a difference in concentration of protons. So they're going to be greater concentration of protons, therefore lower pH. Is going to be in the inner membrane space. And so then the protons are going to flow downhill. Right? So that's a positive concentration gradient. Right? But since the proton is electrically charged, it's also a gradient of charge. And so we can speak about this as a voltage. We won't be talking about the details of the quantitation of it. But in general, we should appreciate that electron motive force, or voltage, or electrochemical gradient, or potential, whichever word you want to use, these words are all kind of pretty much equivalent to each other. What it consists of is a driving force that has components both of concentration gradient and of an electrostatic. Right? pH, I guess delta pH is really the same as delta concentration of protons. But what I mean to say is electrostatic component in addition to a concentration component. Okay. So that's when the textbook talks about voltage gradient or a proton motive force. Right? Probably the phrase that's missing on this slide is proton motive force, or PMF. That's what they're talking about. Okay. So in order to make this happen, we have some new cofactors to know about. So there's three new, you've heard of, actually you've heard of all three of them already, but let's review and look at them. This one you probably haven't seen the structure of yet. This is the compound coenzyme Q. Sometimes we just write Q. Sometimes we write ubiquinone, the UB part of it meaning that it's ubiquitous, so it's like all cells that respire have electron transport chains like this, have a Q. If not exactly like this one, then the molecule will be very similar in structure and will have a commensurate function that's conserved, right? This is a lipid-soluble benzoquinone with isoprenoid side chain for lipid solubility. So here's a 5-carbon unit, so you might recognize the isoprene because it was the building block for cholesterol synthesis and other steroid synthesis. We looked at that for like 1 minute in one slide at the end of the fat selection. Right? But this was what the unit looked like. And so here you see that there's this little number 10, meaning that there's 50 carbons hanging off the end of this thing. Right? So this is, it's got some rigidity to it because it's a double bond. It's also got some floppiness to it, so it's a complicated flexibility issue. But the idea, of course, is that this keeps it in the membrane. Right? So it's lipid soluble, and it's also diffusible. Right? So freely diffusible in the membrane. So the important thing about that is, as we'll see when we look at the overall scheme, we have to move electrons around the membrane to get from one complex to another at a crucial point in the chain. And what moves them is this guy Q. Okay? So if he can't diffuse, then you can't get electrons from what's going to be complex 3 to complex 4. You can't get the electrons there. Complex 4 is where oxygen is. Complex 3 is where all the reducing equivalents from metabolism converge into. But if you can't get from 3 to 4, you're basically toast in terms of being able to actually deliver electrons to oxygen. So this compound delivers the electrons not directly to oxygen, but to the protein